In this video, we're going to be introducing the idea of something called a vertex coloring, which is exactly what it sounds like. We're going to be coloring the vertices of a graph. So formally, a coloring or vertex coloring, we're going to use these interchangeably. So a coloring of a graph is an assignment of colors, and I've got that in quotes, which I'll explain in just a second, to the vertices of G such that every vertex gets one color. Okay, so every single vertex is going to get one color. And if vertices are adjacent, right, so if they have an edge connecting them, then they have to be colored in using different colors. Okay, so let's just see a couple of examples of this. So we want to color the following graphs. Okay, so here I've got several graphs coming up here, and I've got two copies of them because I want to point something out. So first let me get my little color palette here. Okay, so maybe I'll start with green. Okay, so maybe I'll color this vertex green. So that means because this one is green, neither of these two can be green, right? Because rule number 2 says that adjacent vertices have to get different colors. So this is adjacent to this and adjacent to this, right? And these two are also adjacent, which means they need different colors as well. So let me just get, say, blue. I'll color this one blue. And this one is adjacent to both of these two, so it can't be green and it can't be blue. So maybe we'll get something in this yellowish range, gold. All right, and then I come over here. Well, now this one is only adjacent to this gold one so far, so now I can reuse the green if I want. Okay, so let's go back and get a green. I can reuse green here. And again, this is only adjacent to gold so far. So for this green, these two, the only restriction on them so far is they can't be green. So for example, I can reuse my blue up here. And then this one can't be blue or green, but I can reuse this sort of goldish color that I used from earlier. So this is an example of a coloring. So now let me get my black pen back. This is an example of a coloring. Every vertex got exactly one color, and vertices that were adjacent got different colors. Okay, now when you're writing homework or when you're solving these problems, you're probably not going to have 5 or 6 different colored pens next to you. So typically when we talk about coloring a graph, this is why I had colors in quotations above. We really are just going to use like color number 1, color number 2. So the same coloring for this graph would be these two vertices got color number 1, these two vertices got color number 2, and these two vertices got color number 3. Okay, now we're just sort of representing, okay, 1. All the vertices colored 1, those have the same color. We don't actually care if they're green or red or whatever, but they're the same color, and that color is different from color number 2 and from color number 3. So here we used 3 colors to color this one. Okay, so let's go down and check out our next one. And I'll go back and do a couple more here with the color palette. Okay, so I start out and I color this one, right, our sort of goldish color. And so maybe I'll get blue next. So now this one can't be gold and this one can't be gold, but they're not next to each other, so they can both be blue. That's fine. And then maybe I get purple here. So this is only next to blue. So actually I could reuse my gold for this one. That'd be fine. Right, but now this one can't be blue or gold, right? This last one can't be blue or gold, so maybe I'll get my purple for this. And so here is a vertex coloring of this graph. But again, right, I mean, if you don't have access to a bunch of colors, that's totally fine, right? You can just say, oh, see here, the ones that we had here in blue, we really could have just labeled those 1s, right? And then label these 2s and label this one with the 3rd color. So again, this took 3 colors. So let's do one more. And on this one, maybe I'll start with the numbers, and then we'll go back and put colors in so you can sort of see it in the opposite way. Okay, so let's just start here. We color this with color number 1. Okay, now this one is adjacent to all 3 of the other ones, so none of these can be color number 1 now. Okay, so let's just say this one gets color number 2, because those are different. And so now if we think about coloring this, well, it can't be color number 1, it can't be color number 2, so it's going to have to get a new color, color number 3. And if you come to this one, it can't be color number 1, it can't be color number 2, it can't be color number 3, it's going to have to get a new color, color number 4. Right, so if you want to think about what that would look like, right, with actual colors, maybe you label this one green, and this one blue, and this one pink, and this one our sort of goldish color. Now, this graph, we have a name for this graph, right? If you remember, this is K4, right? It's a complete graph on 4 vertices, meaning all the vertices are connected to each other. So it's unsurprising that you're going to need 4 colors because everything is connected to everything else. So that means that every vertex is going to need to get some new color. Okay, so this is the idea behind vertex coloring. And it's not like the colors that I just gave are the only ones. There are a lot of colors for any graph. Okay, so in particular, you don't even have to use the same number of colors. So we're just going to put our color palette away and think about it in terms of numbers. So let's say we started with this and colored it 1. Okay, so that means that this can't be 1, and this can't be 1, and this can't be 1, right? But this one could be 2, and this one could be 2, right? Because they're not next to each other, so it's fine for them to get the same color. Where I hear I mean next to is adjacent. But this one can't be 1 or 2, so it's going to get color number 3. But then the idea usually when you're coloring graphs, you want to try and reuse colors if you can. So you may have noticed that above when I was coloring, I tried to reuse colors if I could. So here, for example, I can reuse the color 1. And then down here, for example, I can reuse the color 3. Right? So here, we were able to color this using just 3 colors. Now, and it turns out that using 3 colors is the minimum number, and that's important, as we're going to see in just a second. But just because I used 3 doesn't mean I couldn't have used more, right? So like I could label these colors 1, 2, 3, and this color 4, and this color 5, and this color 1. Right? This still satisfies my rules for a coloring, right? Every vertex gets exactly 1 color, and every vertex that's adjacent to another vertex, those get different colors. Okay, so we're going to be interested in colorings like this, though, the ones that are sort of most efficient. Right, but you could use any number of colors, right? I mean, you could theoretically, for any graph, give every vertex a different color, and that would be fine. Okay, but the smallest number of colors needed to color a graph has a special name. It's called the chromatic number. And it's denoted with a chi here, this fancy-looking X. So chi of G is the chromatic number of G. So in this case, here we've got a coloring that uses 5 colors, and here we've got a coloring that uses 3 colors, and as I said just a second ago, 3 turns out to be the best for this graph, and we're going to talk more about that in the next video. But here, the chromatic number of this would be 3, because you can't color it using just 2 colors. Right? For example, if you think about just this triangle right here on the left-hand side, those are all 3 going to have to get different colors. Right, because they're all adjacent to each other. Okay, so that's the chromatic number. And then the last thing I want to say in this video is, if it's possible to color G using K colors, we say that G is K colorable. Right, so like the graph that we were just looking at above was 3 colorable and 5 colorable, because we just saw we just saw 2 colorings where we used 3 colors and 5 colors respectively. Right, so this tells us that it's 3 colorable. This tells us that this graph is 5 colorable. And in general, right, if you can color it using 3 colors, then you can definitely color it using 4 colors, or 5 colors, or 6 colors, or 7 colors, right? Because the sort of smallest number, the chromatic number, is the most restrictive, right? You could always go back and change something in a minimum coloring, right? So like this, I could go back and change this 3 into a 4. Now there's no 4s anywhere else, but of course there's no way that this 4 is going to be adjacent to any other 4s, right? Because I just use a brand new color. So now it's 4 colorable. right? Or I could go back and change this 2, right? And say, oh, I want that to be a 5, and now it's 5 colorable, right? And I could keep changing these things. So the comment that I want to make here at the end is that if a graph G is K colorable, then G is N colorable, for all N greater than or equal to K. Right, so you can always use more colors. And by the way, you don't necessarily need to use all your colors. So even though this graph only has 4 vertices, we could say that this is 7 colorable. Okay, so maybe we use our colors 7, 5, 4, and 2. And this is 7 colorable because if I have my palette of 7 colors, 1, 2, 3, 4, 5, 6, 7, so this you can think of as your palette of colors. And if I can label all the vertices in this graph using only these colors and get a coloring, right? Our 2 rules, every vertex gets 1 color and nothing that's adjacent gets the same color, then that's a coloring. So this is 7 colorable, for example, or it's 100 colorable, right? Like we sort of don't care about the upper limit. We're really only interested in the lower limit. And that lower limit, that smallest number of colors, is called the chromatic number, and we're going to talk a little more about that in the next video.